Good day, and thank you for joining us. My name is Boyd Ramsey, and I'm here representing the International Geosynthetic Society Technical Committee for Barrier Systems. The title of this session is Geosynthetic Barriers, and we're glad you joined us today. I would also like to recognize my co-reviewer, Jonathan Shamrock, who is the chairman of the IGS Technical Committee on Barrier Systems. He helped me with reviewing the papers for this session. Just a couple of things to note before we start the presentations. You'll have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. These questions will then be sent to the presenter and they'll answer them as soon as they're able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you fill out the survey for the sessions that you attended. Please note that you will need to know and include the verification code shown in this session to verify that you did attend the session and to ensure that you received the proper credits. Again, thank you for joining us, and please enjoy the presentations.
Hello everyone, my name is Jianan. You can call me Nick. I'm an assistant professor from University of Central Florida. And today I'm going to give a presentation on the using of bentonite polymer composite geosynthetic clay liners to contain bauxite liquor and co-combustion product leachates. In this study, we're evaluating the compatibility of BPC GCLs to two types of leachate. That is one from red mud waste management that is called bauxite liquor. The other one is leachates from co-combustion products. So before we go over this presentation, I want to first acknowledge my co-authors, Dr. Benson, who is the Dean of University of Virginia, and also the advisor on this research. Also Sarah Gastisis from Geosynthetic Consultants. And she's formerly a PhD student at University of Virginia. So first, we want to give you some background on what is red mud. Red mud is the industrial waste from alumina processing. So in this process, bauxite is added into the manufacture process with caustic soda. So the key point is using the high pH to digest the aluminum to purify the aluminum. In the system, in the process, a waste is generated, which is called red mud. The physical features of this material is fine grain material and also like a mud, and its property, because we use caustic soda, this material has high alkaline characteristics. So that means it is very corrosive in the environment. So aluminum production is worldwide, especially peak out of 2017, the statistics of this year. And we can see China, Australia, and Brazil are the top three countries produce the aluminum, and also the red mud generation is very high for these countries. But red mud disposal is worldwide still, because if we produce red mud, we need to care about this material. Because this material is very corrosive, as I mentioned, its pour water, which is called bauxite liquor, should be appropriately managed. So especially when we design the containment facilities, we need to care about the leakage of this leakage of the bauxite liquor to make sure there's no secondary contamination. So typically red mud is contained in impoundment or a reservoir. So here is a picture I took in China and during my visit. And here the pumping in the red mud with slurry forms, and the red mud, usually the solid will settle down to the bottom, and you have a lot of liquid on top and also inside the red mud. So here, a liner system is usually constructed to contain this liquor to avoid any environmental contamination. So design this liner can be very critical. Usually, the design is for this liner is a composite liner system, which means you have a geomembrane plus either soil layer or geosynthetics. So for the soil layers, it requires the K, which is hydraulic conductivity, less than 10 to minus meter per second, and thickness can vary over different countries' specifications. For example, in China, it usually do 1 meters. Sometimes because the subgrade condition is or the soil condition is not that good, it requires thicker soil liner there. Also, typically or nowadays, many of the measurement facilities are using the geosynthetic liners, especially using bentonite polymer composite geosynthetic liners. Similar situation for the for the CCP, which is co-combustion products, which is right now a very hot topic in the US. In the 2015, the coash rules requires the newly constructed coash impoundment and landfill, they should use the composite liner system. So this liner design follows the RECRA subtitle D landfill design, and especially for this liner, we have the composite liner, which is 1 layer of geomembrane plus 0.6 meter of soil liners, or you can use geosynthetics, that is GCLs, as an alternative liner system. Especially nowadays, GCLs have been widely used to contain co-combustion products. The research we conducted previously also compared the performance of sodium bentonite and BPC GCLs. So this study, because in the recent years, the products from manufacturer, the BPC changed, and also the chemistry may change for bauxite liquor and the CCP leachate. We are evaluating the compatibility of these BPC GCLs to red mud and CCP leachates. So in this study, for a better understanding of the compatibility, we have 3 questions. First is to understand the chemistry of bauxite liquor and CCP leachate. Second is to understand the hydraulic conductivity of the BPC GCLs to bauxite liquor and CCP leachate. Third is, after we understand this hydraulic behaviors, we want to know the controlling mechanisms of the hydraulic conductivity of BPC GCLs. So based on our previous experience, we know the different site and also different manufacture process, different minerals from the original material can make the leachates vary a lot. So in this study, especially for bauxite liquor, we sampled all across the world. So many countries are included in this study. So these countries include US, Brazil, Poland, Saudi, UAE, Australia, and China. So we took the sample and shipped the sample back to the lab and run the cations and the anions concentration. And also we also evaluated the pH and electrical conductivity. So we find out actually all this leachates, all these bauxite liquors, they are high in pH, especially this pH between are all between 12 and 13, and some of them are close to 13. Also, the ionic strength is the measure of the total concentration of ions in the bauxite liquor. So the higher means you have more dissolved phases in the liquor. So in this case, the geometric mean of this ionic strength is around 500 to 600 millimolar, while some of the bauxite liquor can be strong, which is 1.5 molar. We also sampled several power units across US and take the leachates back to the lab to run analysis, and which will help us to understand the leachate chemistry of CCPs in the US. Similar to bauxite liquor, we evaluated the major cations, anions of the CCP leachates, and also pH and electrical conductivity. One thing we find especially interested for the GCL study is usually we use the relative abundance of monovalent and polyvalent cations and ionic strengths to relatively compare the chemistry of the leachates. So RMD is a measure of the relative abundance of monovalent cations to divalent cations. So lower means you have a higher tendency for the cation exchange. So in this study, the closed symbols are samples for this study, and open symbols are a database from the EPRI report. Dr. Benson and I worked on in 2015. So actually, we can find out the chemistry of recent years doesn't change too much. I will see the agreement is good, except one of the leachates is higher than whole, which is around nearly 700 millimolar. So for the BPC GCLs, it's designed to improve the chemical resistivity and reduce the hydraulic conductivity of the sodium bentonite. So in this study, we evaluated 16 BPC GCLs for bauxite liquors. So the number indicates the polymer loadings of these GCLs, and the method is measured by the loss on ignition method created by Dr. Scalia in 2014. Similarly, for the CCP studies, we used 7 BPC GCLs, and the number also indicates the polymer loading. Beside these GCLs, we also tried sodium bentonite for both bauxite liquor and the CCP leachates. Yeah, so when we start talking about the results, we want to give you some concept model for the polymer clogging, which is our hypothesis on the mechanism of the BPC GCLs. So as we mentioned, the sodium bentonite is chemically sensitive to the leachate. So when you have dilute leachate, you will often see the sodium bentonite granules are swollen, and you have low pore spaces for the flow to occur. While when you have high ionic strength or higher divalent cations in the leachate, you will see a sodium bentonite granules that have a shrinking structure or a granular structure that leaves macropores for the flow to occur. The polymer clogging, polymer BPC GCLs obviously is designed using the polymer to form hydrogels in between these pores and create low hydraulic conductivity under high ionic strength leachate, where the sodium bentonite is not swollen as you expected. So in this study, we used the traditional falling head flexible wall permeameters to evaluate the hydraulic conductivity of the BPC GCLs, and also we took out the bentonite to run swell index, and the microstructures were also analyzed by SEM with EDS. So here's the results of the hydraulic conductivity of BPC GCLs to bauxite liquor and CCP leachate. First, I want to mention when we used sodium bentonite GCLs, it shows higher hydraulic conductivity under higher ionic strength of the leachates. At the same time, when we compare this result with the BPC GCLs, you can see the BPC GCLs usually has lower hydraulic conductivity. Lower means 2 to 5 orders of magnitude. Especially for the CCP leachates, the hydraulic conductivities are all lower than 10 to minus 10 meter per second for all this to all these leachates. Still, there are some increase in hydraulic conductivity at a high ionic strength range for bauxite liquor. I will cover this in the mechanism discussion. So we want to understand the controlling mechanism of these GCLs. Especially first, we compare the hydraulic conductivity with the swell index. So as we expected, the hydraulic conductivity is not correlated with swell index. This is in consistency with our previous study. Because the polymer, what we on our understanding is polymer is playing a big role in this game. So when we compare the hydraulic conductivity with polymer loading, we see the polymer loading actually, when you have sufficient polymer loading, it will better maintain the hydraulic conductivity. Especially for the bauxite liquor, polymer loading, if it's higher than 8.1, you will have hydraulic conductivity generally lower than 3 times 10 to minus 11. Similarly, for the BPCs to CCP leachates, when the polymer loading is 5.8%, so you will see the hydraulic conductivity is usually less than 3 times 10 to minus 11 meter per second. Also, I want to point out that at a similar polymer loading, you will see some differences in the hydraulic conductivity from this slide or the previous slide. So this is likely due to different permeation liquid or different types of the polymer that is in the BPCs. So far we know the polymer is playing a big role in this game. And we want to see the microstructure, how this polymer affect the pore species. So we hydrate BPCs with DI water and bauxite liquor to see the differences. First, we see if the polymer is in the DI water and it hydrate well, so you can see the highly swollen structure, and you can imagine this polymer when it's fully swollen, it can clog the pore spaces very easily and very, very well. Actually, you can shoot the EDS on the polymer and clay to differentiate which one is clay, which one is polymer. On the moderate strengths of bauxite liquor and CCPs, you should expect a similar image as the DI water. But if you have a higher or stronger bauxite liquor, as we mentioned earlier, you can still find high hydraulic conductivity. The reason is this polymer structure is swollen structure is of sense. So here you can see the open pore spaces that is happening where no actually polymer is clogging this area. So that generated high hydraulic conductivity. Here comes to the final of this presentation. So we want to summarize what we learned and make conclusions. So first conclusion is that the chemistry of the bauxite liquor and the CCP leachate is widely site dependent and need to be considered in designing the liner system. Especially we find out the bauxite liquor is very highly alkaline, and also some of them may have high ionic strengths. This leachate chemistry can strongly influence the hydraulic conductivity of sodium bentonite GCLs. But you will often find BPC GCLs can have much lower hydraulic conductivity than sodium bentonite GCLs, and this should be a good alternative for soil liner or sodium bentonite GCLs. And then the mechanisms controlling hydraulic conductivity for BPC GCLs is different from sodium bentonite GCLs. Usually sodium bentonite GCLs quite depend on the swelling mechanism of swell behavior of the bentonite, while the BPCs is highly rely on the polymer where the polymer loading, the characteristics of polymer can be very important. So this is final slide. I want to thank you for your attention and listening to this presentation. At the same time, I want to acknowledge my co-authors, Dr. Benson and Sarah. Also, especially for our sponsors from the industry and also the Research Institute. If you have any questions, please contact me by the email, and I would like to answer your questions. Thank you very much.
Hello, and welcome to the 2021 Geosynthetics Conference. My name is Glenn Tepfer, and I'm going to be presenting the fundamentals of geomembrane seaming and weld quality. We'll begin with an introduction to thermal seaming. As the name implies, heat is the primary source used to join the panels together using the thermal welding method. As you can see in the photo on this slide, in the field, generators are a primary source of the electricity which create the heat. There are three commonly used methods of thermal welding: the hot air, pictured on the left, the fusion, pictured in the center, and the extrusion fillet, pictured on the right of this slide. Thermal welding is used on a variety of materials for welding in the field or in fabrication shops. The materials are broken down into non-reinforced, which have no scrim, and reinforced materials which have a scrim in the center, primarily for the purpose of adding strength. On this slide, you can see examples of the different materials that can be welded using thermal welding methods. Creating a sound weld for any material requires a correct combination of heat, speed, and pressure. There's some examples on this slide: fusion welding PVC on the bottom left, extrusion welding HDPE in the center, and hot air welding of a woven coated on the bottom right. The successful combination of heat, speed, and pressure should result in a homogeneous weld that does not damage the geomembrane. As you can see in the diagram, heat, speed, and pressure can be illustrated using a triangle for each of the three components. If you look within the triangle, it shows clearly that the heat, speed, and pressure for PVC, as illustrated by the gold circle, is different than the heat, speed, and pressure required for welding the polyethylene materials HDPE and LLDPE. If you look further within the circle, there's always going to be a sweet spot where you have a better setting that's going to give you your best quality welds. Unfortunately, our industry often looks at welding as a plug and play, where all you have to do is get your welding machine, put the liner in, let it run, and you're going to get a good quality weld. Well, that's not the case. Minor deviances in either heat, speed, or pressure can result in significant geomembrane failures. And those failures could be short-term, where they'll be obvious during construction, or they could be long-term, where they may degrade over time because of improper welding and fail 5 to 10 years down the road under stress. What many people fail to realize is that the quality of the weld is not always the end result of the field work or the quality of the field work itself. The quality of the weld begins long before that, and it's illustrated in this diagram I like to call the pyramid of success. It begins with the owner involvement and accountability before the project's even designed, picking the right vendors, the people to design the project that actually have a background in geosynthetics, and then getting good specifications, selecting the proper materials, proper equipment. Vendor selection makes a big difference, and then finally the field work aspect. All result in the final end quality of the weld. Now we're going to look at the heat, speed, and pressure controls for each of the thermal welding methods I listed before. There are two types of hot air thermal methods: the mechanically propelled and the handheld. This slide deals with the mechanically propelled. In the mechanically propelled, the machine will have an adjustable setting for heat, an adjustable setting for speed, and the pressure, depending on the manufacturer and model, may be adjustable or it may not be adjustable. The second hot air thermal welding method is handheld devices. And on these devices, there's usually going to be an adjustable setting for heat, but that's the only setting there's going to be. As you can see in the photo on the left, bottom left, if you look to the left of the guy with a glove where his hand is, there's a red knob. That's usually going to be your adjustable heat setting. But you can see the speed and the pressure are going to be how fast the guy moves, that nozzle, and the pressure is going to be his foot sealing the geomembrane panels together. In the upper right, same thing, except that they're using a hand roller for the pressure. For the thermal fusion, you're going to have a heat that's going to have an adjustable setting, as you can see in the picture on the right. The 700 is your setting. The speed also has a setting, and the pressure. Some machines, again, will have a setting that correlates directly to pressure, and some will not have an adjustable pressure. The extrusion fillet method is a more complicated method, as there's a lot more manual preparation before you even put the actual extrusion weld down itself. Because of that and the type of weld, it's often considered an inferior weld to fusion, but it must be used where fusion cannot be performed. If you look at the pictures, it shows these manual operations. There's a heat tacking, but in this case, it's not your primary weld. It's using the hot air gun, but again, it's just heat tacking the sheets together. Then there's abrasion on some materials, reinforced materials, and there's a few others that don't get abraded. And then finally, the welding. Extrusion fillet has two sources of heat. The first one is just a preheat ahead of the nozzle of the gun. The barrel is where the welding rod comes out, and both of those are adjustable settings. In the barrel, you're trying to melt the extrudate rod so that it is the right temperature for blending with the geomembrane. The speed is going to be how fast the operator moves, and the pressure is going to be manual. It's going to be the weight of the gun and whatever pressure the operator is putting on the weld. So you want to have a firm substrate below it. Welding over a wrinkle is a bad idea because it doesn't have a firm substrate, and it results in an inferior weld. This picture illustrates the preheat I talked about on the previous slide. It's a close-up picture where you can see the preheat ahead of the barrel, where the welding shoe is there. The white is the welding shoe, Teflon welding shoe. And one of the concerns here illustrated is the angle at which the preheat is aimed. If it's too far of an angle, your preheat's not going to be as hot and it's not going to warm the geomembrane up properly. And that really is especially true in cold weather. This slide shows a summary of the different welding methods we discussed and how the temperature, speed, and pressure are adjusted for each of those welding methods. In this section, we're going to look at how material type can impact weld quality. Designers are going to choose the material used on a project based on resistance to chemicals, compatibility with water, resistance to stress, reinforcement, etc. These materials will have different chemical compositions, which ultimately change the requirements for welding. This table shows the minimum and maximum welding temperature range for different geomembrane formulations. For example, if you look at HDPE, degrees Fahrenheit, its range is 600 degrees to 850 degrees Fahrenheit, whereas the next line, PVC, is 330 degrees to 700 degrees Fahrenheit. It also shows that reinforced materials as designated with a -R, such as PVC-R below it, are welded typically at the same temperatures as the non-reinforced materials. Even materials of the same chemical composition vary widely. If you look at HDPE, there's a bunch of varieties. The thickness can range anywhere from 20 to 120 mils. The top and bottom sheets may have a texture, and it could be smooth, it could be textured smooth, textured. There's differences in the texturing. There's a smooth welding edge in the machine direction, heavy texturing or regular texturing, calendared texturing versus impingement, which are both processes of the manufacturing. There's conductive sheet, and there's different colorations. Each of these variances is going to play a role in that welding triangle we talked about earlier. We talked briefly about reinforced materials a couple slides ago. When welding the reinforced materials, it's important that the scrim is not damaged, as a scrim is often there for strength and puncture resistance. If it gets damaged, it will not have that strength. In summary, each of the differences in material properties will somehow impact the welding window and the proper heat, speed, and pressure, and they need to be considered during the design and compilation of the technical specifications. Now we are going to look at how design can impact weld quality. One of the biggest issues we see in the field during construction is the constructability of the designer's design. A lot of times things just aren't constructible as they're designed. These pictures here illustrate that. If you look at the one on the bottom left, there's low pressure when extrusion welding vertically. Obviously it's a challenge, as you've seen the pictures of the extrusion welding method, to hold that machine and equipment vertically. The center one shows insufficient clearance for welding around the pipe, and the third one shows that there's a hard to get at area where there's again going to be low pressure. The designer needs to account for all of these and understand the limitations, and that's where constructability review by a geosynthetics installer is a good idea, and we recommend it, and we've seen it done on several projects, and it's prevented a lot of issues in the field and made them more constructible. These constructability or peer reviews also help in finding the best design methods. For instance, geosynthetics installers are often aware of other products that are out there that designers may not be, especially if they're not designing a lot of geosynthetics projects. If you look at this one, this constructability review suggested prefabricated corners and improved the weld quality significantly. The designers also need to be aware of alternatives to traditional methods, such as the use of a Dremel tool to abrade inside corners where a typical grinding disc will not fit. The design also needs to consider the reduction of inferior weld types. There's usually going to be a primary seam method and a repair method that are going to be different. Your primary seams are going to be the bulk of your seams. If you look at the PVC method, thermal fusion is going to be your primary method, but the repairs can only be performed by chemical or adhesive, which are very inferior compared to the thermal, so you want to minimize the amount of that seaming. Another method to minimize the amount of even the primary seaming, as shown in the picture below, is wider panels. Wider panels reduces the amount of primary seaming, but also there's going to be less repairs, less intersections, so you greatly reduce the amount of inferior welding as well. As a designer, you also need to avoid falling into the pitfall that believe in welds do not fail. Not only if welds are placed where they cannot be welded, there's always going to be variables on the project such as dust, moisture, things that aren't planned for that can cause welds to fail that we'll be talking about later. So you need to make sure that in the design the welds can also be testable and non-destructive as well as destructive testing to make sure that the welds are of good quality. In this section we will look at some of the impacts that technical specifications can have on weld quality. One of the biggest issues we see with the technical specifications is that they do not go hand in hand with the design. A lot of engineers cut and paste specifications and they make no sense and cause delays in the field. The other thing that's common is that they do not empower the quality assurance personnel to do their job properly and enforce and remove inferior welds. In order for the heat to remain constant, you need to have a good generator, and oftentimes we see that the technical specifications do not address adequate power supply. And if you use an inferior generator, an improper generator, you're not going to have the proper balance and continuity of the heat to get a consistent weld. Another often overlooked area is the power supply cords. Many people don't realize that the manufacturers have recommendations as shown on the page here for the generators, as well as for how many connections and the length of wire cord that can be run. Following these recommendations is key and critical to obtaining good welds and consistency in the welding. Because consistent power supply is critical to the welding process, it's important to know if you're getting that consistency or not. Ideally, welding machines would have devices that would allow you to monitor the current that's arriving at the machine throughout the welding period. Another area we see lagging in technical specifications is dealing with material interface and understanding how that relates to the quality of the weld. As shown in the picture here, there's a smooth welding edge on this textured sheet, and that allows the overlap. The overlap is your interface area, the bottom of the top sheet and the top of the bottom sheet, what those two materials are. In this case, it's a smooth and smooth, but it could be a textured if you're on a cross machine, a butt seam, and textured smooth might be possible at other areas as well. And each of those combinations of interfaces is going to change the welding parameters for that particular interface. This table is here to show the difference between textured and smooth interfaces. If you look at the bottom of the table, you can see that if you were welding two sheets of 60 mil smooth together, you're roughly going to be at 120 mils that you're welding between the rollers. When you get to the double-sided, you could be close to 200 mils of total thickness. When you're using these different thicknesses, obviously that's going to mean different heats required for the weld, different speed, and ultimately different pressure as well. And the installer needs to be making those adjustments if they're going to get a good weld in the field between materials. And this table illustrates that there's different settings used for almost the same ambient temperature between machines and between interfaces, the predominant one being the speed was changed in this case. In a study that I participated in, we looked at failures by interface, and you can see smooth averaged 4.3%, but once you started getting the textured component added, the textured failure rates went up, and that's a result of the difference in the welding conditions changed by the texturing interface. In that same study, we also looked at when destructive samples were taken on a textured interface and they were tracked to a smooth interface or another textured interface. In all the cases we looked at, when they were tracked to a smooth interface, they immediately passed. And so there needs to be some guidance on how to make sure the other textured seams are not being missed and they're being accounted for somehow. Perhaps the most obvious is weather conditions. They're obviously going to have an impact on the welding, the heat, the speed, and the pressure, and they can change several times throughout the day. So it's important for the specifications to give the QA the flexibility to make sure there's other options for making sure the welds are valid. Trial seams are a great opportunity to evaluate the welds beyond peel and shear. You can look for off-center welds, overheating at tees, make sure the material is welded on top of the proper material. It's a great opportunity, but often it's not used because it's not in the specifications. End coupons are another way to get a real-time glimpse into the quality of the weld and should be put in the technical specifications. Destructive seam testing protocols should include the testing of repairs. The amount of inferior footage adds up quickly on projects. And for example, the Zero Leak Palo Verde project I was involved with would not have been zero leaks if we did not do destructive testing on the extrusion welds. The owner should specify a reasonable expectation for maximum failure welds of destructive samples. They should be monitored daily, and if the failure rates are exceeded, the installer should stop and not do any more production welding until they can figure out the source of the problem. Technical specifications should minimize inferior weld types. There's different ways to do that. One is, picking a length where that length cannot be exceeded in repair. And if it is, you have to use the primary welding method, for instance, extrusion versus fusion. If you do that, the results speak for themselves. You can really minimize the amount of inferior welding that's out there if it's just planned for and addressed. We're going to look at the impacts the geomembrane installer has on weld quality. Obviously, the installer plays a huge role, especially their welding operators and their equipment and their familiarity with the material. Getting certified installers is a bonus, and checking references on materials and similar projects is essential. The proposed panel layout can tell you a lot about an installer, especially if they don't have any butt seams showing. This is a good panel layout. They show the butt seams, and that's something that should be reviewed by the engineer to make sure that the amount of inferior seaming is being minimized. Now we're going to look at how welding equipment impacts the quality of the weld. Wedges get their name from their shape. They are designed to heat up the geomembrane as the top and bottom sheets pass over them for both the fusion, hot air welding methods. They are made of different material compositions. This slide shows some hot air wedges and configurations. As I mentioned, wedges can come in different material compositions such as stainless steel, copper, and porcelain. The use is dependent on the material. Copper is going to give you your most uniform heat transfer, but it's also going to react with PVC, so it's not a good choice for PVC. There's also different shapes, such as a short and a long wedge. Once the heated material passes through the wedge, they're going to be forced together using the nip rollers, and like the wedge, the nip rollers come in different compositions, such as stainless steel, rubber, silicone, and HDPE. There's also different knurls, such as fine or coarse, and there's also different edge roundings, and the edge roundings are often not specified, but can make a huge difference, especially on thin materials. This slide shows some different impressions left by the different nip rollers of different manufacturers. Evaluating the impressions left by the nip rollers on a completed seam can be key to identifying problems. The photo on the left shows adequate pressure. The photo in the center shows light pressure, which is going to be an issue. And there's an obvious issue with a photo on the right where the pressure is cutting through the liner, so it's way too much pressure. The extrusion welding shoe should also be evaluated during the field installation. As shown here, the extrusion welding shoes come in different sizes and shapes for different reasons. One of the big things that happens in the field is they're often modified by operators with a grinder, and that can greatly alter the weld quality. Data recording and smart wedges are a new and developing technology. It's important to understand the difference, and that data recording is simply that, it just records, whereas a smart wedge has a processor that regulates the machine as it goes along to keep the electric current consistent as well as its heat, speed, and pressure. Calibration should also be required in order to have a reference. We'll now look at construction quality assurance and its impacts on weld quality. I believe this quote says it all. Quote, "The first dollar I would spend on a project would be on construction quality assurance," unquote, by Boyd Ramsey of Ramsey Consulting. There are numerous studies out there that also support Boyd Ramsey's statement about the value of CQA personnel. The CQA personnel are the eyes and ears of the project, and they need to be out there observing and watching what's going on so they can identify issues and stop them. CQA personnel need to be observing everything, and visual assessment cannot be understated. In this example, the technician is looking at coupons from trial welds. In the case of trial seams, there's far more to look at than just peel and shear. In this case, beveling, which was properly performed in the sample on the left and improperly performed with a sample on the right. Even if the sample on the right passed peel and shear, that sample should be rejected and the operator made to redo a new trial seam. It's important to have technicians present when the actual extrusion welding is being performed because you cannot see conditions like missing grind once it's been welded. So how do we mitigate the issues with heat, speed, and pressure to get good welds? By understanding the welding process and the components of heat, speed, and pressure, mitigation can occur and should occur at every step along the way from inception through completion of the project. Conclusion. Thermal welding methods are highly advantageous and yield outstanding results when heat, speed, and pressure are properly controlled and monitored. Thank you for your time, and I hope that you've taken away at least a few new things from my presentation. If you have any questions, feel free to reach out to me with a contact